rate. So you can see what happens with the tab during a single collision, and there's also a tab for multiple collisions. Let's see what we can learn by looking at the tab involving many collisions. So when I'm thinking about a single collision, I'm thinking about the relevance of the Arrhenius equation, how the activation energy is important to as it influences the rate constant. And the temperature is also important as well. For the activation energy, I'm thinking of this barrier that needs to be overcome to move from, if we want to consider the reactants to the products, or back and forth from the products back to the reactants. In both cases, there's a particular barrier where I need sufficient energy to allow the collisions to make it overcome that barrier and move from one side to the other. I'm thinking how a smaller activation energy leads to a larger rate constant. That's our symbol, small letter K. And we need to think about the energy of activation here in both directions because it's a barrier that is blocking as I go left to right and also right to left. Those are all insights that I came away with when I was looking at a single collision, and by changing the temperature, changing the kinetic energy, I could change what the total energy was. Let's now look to see what happens when we have many collisions taking place. So in this case, instead of just having a small set of atoms and molecules in the container, I'm going to now add many different ones. So we have many different atoms present. To help keep track within this one, I've added a bar chart here. So this will show the total that we have that's shown in this representation. Now it adds it up for us. We can also see that listed on the far right where it shows the current amounts. We have a reaction that's going to take place. We can keep track of the current amounts, and here's the energy level diagram that matches up with the reaction. If you recall, the energy here, that matches up with the temperature. So I'm going to set up the sim so it matches the conditions that you see right here. I want you to make a prediction. What will happen when 10 of the BC molecules are now added to this container at this temperature? Taking all the information that you have right here, what's going to happen when we have 10 of A and 10 of BC at this particular temperature? Okay, let's check. So I'm going to begin by adding 10 of A. We'll get to that target temperature. The current amounts here in the bar chart, that's a helpful way to keep track of what happens. We'll add 10 of BC. Okay, I'm beginning to see some product form. I'm beginning to see the reaction taking place to some extent. As time goes on, I'm seeing that the relative numbers, they're definitely not all A and BC. I have some products formed there. A few different observations here. This reaction took place even though the total average energy was less than the energy of activation. The reaction did not stop. I saw over time that those relative amounts were still being adjusted. And it sure looks like that the concentration of A and BC, the left-hand side, was greater than the concentration of AB plus C. I'd say that the reaction is favoring the left-hand side. Favoring the left-hand side, I would say that's leading to a higher concentration of those reactants. So a key thing here on the reaction taking place, even though the total average energy was less than the energy of activation, a key feature there is this is describing the total average energy. To make that clear, let's zoom in on this feature right here. I'm just going to see what happens if we're looking at these particles A. If we raise the temperature, the total average energy is going up. But that doesn't mean all of the particles have the same kinetic energy as each other. Some are moving a lot faster, and some of them are really close to being at a standstill. That gives us a key insight here. It gives us an insight for how the reaction can take place, even when the total average energy is below the energy of activation. Because in order for the reaction to take place, we're not interested in the total average. We're interested in the energy that accompanies a particular collision. And even if the total average energy can be below this threshold value, some of the collisions are higher and some of the collisions are lower. It's those that are taking place that are affecting the rate. When we have multiple collisions, the rate constant increases as the kinetic energy goes up. And it increases quite rapidly as the fraction of the collisions exceed the energy of activation. We have a distribution of kinetic energy for the particles at one temperature, and if we raise the temperature, notice how the profile shifts. And by shifting that, we can have more of the particles that are above the energy of activation threshold. Here we see on the left-hand side how changing the temperature changes the rate constant. Increasing the temperature is going to increase the rate constant, small k. Okay, make a prediction right now. This is how I'm going to set it up. I'm going to set it up where this is the total average energy, and I'm going to have equal amounts of all of the particles in the container. A, B, C, A, B, and C. So I'm going to start out with some that we would consider reactants and some as products that are all going to be in the container in equal amounts to start out with. What's going to happen when we run it now? Will the concentrations remain equal? Will a reaction take place that's going to lead to more on the left-hand side, which is the A plus BC, or more on the right-hand side? Make a prediction. Let's check it out. Okay, I'm seeing a reaction take place. I'm seeing the amounts shift a little bit. And notice that they shifted, and there's more that would be considered on the left-hand side than on the right-hand side. Now, when we say left-hand side and the right-hand side, as we see with this image, they're all in the same container. That idea of left-hand side or right-hand side, that's our bookkeeping to try to make sense of it for the chemical equation as we've written it. But let's not fool ourselves. There's not a left-hand side of that box and the right-hand side of the box that is somehow different. So as that proceeded right there, it definitely looks like I put more on the left-hand side of the reaction, more of A plus BC. I started out with equal amounts, but it seemed to settle into these particular values. If we can make sense of that within this image right here, we started out with equal amounts. If we have the particles, though, if you want to say go down the hill and end up with the ones with lower potential energy, they now face a larger energy of activation to come back out and go left to right. In a way, it's easier to overcome this barrier going from the right to the left than it is from the left to the right. And that's leading with more particles being found here on the left-hand side. Let's see if temperature is at all important in this process. We saw that if we started out with equal amounts, we ended up with more particles being found on the part of the energy diagram that was at lower potential energy. Let's run it now, and what I'm going to do is I'm going to have a large number of particles, and instead of tracking it through with the numbers, I'm going to have it in a strip diagram so we can see the relative amounts. So I've got a lot of the different particles being shown. Given this total average energy relative to the profile, I'm beginning to see a separation. The separation right here, I have more higher concentration of A and BC and a smaller concentration of the line that's corresponding to the right-hand side. That seems consistent with what we just were discussing. We're having a higher concentration for the part that is at a lower potential energy. When we have this as the temperature as the total average energy. So that's consistent with what we just saw. And it looks like it's settling into those values. Yes, there's a little bit of fluctuation, but it's settling into those values. Now we can alter the temperature. If we lower the temperature, it seems like it's exaggerating that difference. By lowering the temperature, I have exaggerated the difference, and I have even more that are being found in this AB. Excuse me, I have even more that are being found in the line that corresponds to the A and the BC, and even less that is found for the line that's corresponding to the right-hand side. By cooling it down, by lowering the temperature, I have even more particles that are getting stuck on this lower potential energy side. It became even more difficult to get over the barrier. The way I think of it is I have a back and forth that's going on, but when I have very little energy right here, if they find their way to this left-hand side, very few are going to have enough kinetic energy to be able to overcome the barrier. Now we can raise the temperature as well. If we're looking at the relative amounts, they're definitely changing. Let's keep raising it. Okay, now we're well above the energy of activation. And notice how the relative amounts have come really close to each other. In a sense, if I'm well above the energy of activation, it doesn't even really matter that it's there. I'm able to go left to right or right to left just as equally. It's just as easy in both directions. So I see within that case, I see a real leveling off and the concentrations becoming quite similar. Yes, there's still some noise within here, which has to do with the individual collisions. But the relative amounts quite similar to each other. If we cool it back down again, what side is it going to favor? If I cool it back down again and I'm taking the total average energy lower and lower, I see once again that I end up with more of the ones that are lower potential energy and fewer that are found at the higher potential energy. So really, how can we begin to make sense of that in terms of the rates? Let's say we're looking at these two reaction progress diagrams. I can be going from A to B. That looks like an exothermic reaction. Or I can be going from C to D. That looks like an endothermic one. What would happen if we change the temperature for these? How is it going to affect the rates? Here's an equation that describes how you can calculate a particular ratio involving the rate constants for a particular energy of activation and the temperatures that are involved. If I'm looking at the different choices for how things would change, within that bottom right there, would a rate go down if I increase the temperature? That doesn't make any sense to me. If the temperature goes up, the average kinetic energy has gone up. The collisions now are more energetic. I have no reason to think, well, how would that lower the rate? That doesn't make any sense with my Arrhenius equation. So I'm going to get rid of that choice right there. So then the next question is, I see differences right here. In this case right here, this is a small energy of activation. And in this case, it's a large energy of activation. So the real question is, which of these is affected more when I change the temperature? It turns out that this is the correct answer. An increase in the temperature definitely increases the rate constant, small letter k. But when the energy of activation is larger, the k value is going to increase more. We initially have very few particles with enough kinetic energy to overcome the barrier, and by increasing the temperature, increasing the kinetic energy, that proportion dramatically increases. That's what we saw when we were looking at the sim just a moment ago. When we were at the lower temperature, we found that we were favoring the side that had a lower potential energy, and its concentration was much higher than the side with the higher potential energy. It was getting stuck at the bottom of this reaction coordinate diagram. By raising the total average temperature, as that green line moved up, both of the rates increased. Both the rates going left to right and right to left, but the one with the larger energy of activation increases more, and that's what shifts the concentrations. When we have it where the system has run for a while, we would say it's reached equilibrium. All the particles are still stuck in the box right there, and there's a back and forth. Let's say these were the equilibrium amounts. You reached this point. Do you think that this started out with all A and B, C? Did it start out with all A, B, and C? Or does that even matter? What's your thought? I think the best answer is it doesn't matter. You're going to reach these relative values. You're going to reach a value where you have more that have the lower potential energy. It doesn't matter if you started out all on the left-hand side, all on the right, or a combination of some kind. This will be the finish line. But now what would happen if you took that and you changed the temperature? What if you took these amounts and you lowered the temperature for your box and the total average energy went down? Or if you took your system there and you added heat to it and the whole total average energy went up, how do you think these diagrams would change? By lowering the temperature, you begin to have more of the particles that are stuck at the lower potential energy, and those values begin to go up, and the ones at the higher potential energy decrease. And we have the opposite taking place as we begin to raise the temperature. As we begin to raise the temperature, it becomes less and less important that you have this differential in the energy of activation, and they get closer and closer together. All of these are showing an endothermic process if we read it going left to right. Increasing the temperature of an endothermic process shifts the equilibrium to the product side. That's what's being shown here with the leftmost figure. We begin with the lower temperature, and then as we increase the temperature, we go from that leftmost one to this one on the far right-hand side. So we really are saying, let's change the temperature progressively here. And by changing the temperature progressively, I see that I'm shifting more and more to the product side for these endothermic reactions. How about this case right here? Let's see if we can bring all the ideas together. This is an exothermic reaction if I compare the left-hand side to the right-hand side. I'm going to add in roughly the same amounts of all of the different particles. After adding all of those, I'm going to begin to cool it down by lowering the temperature. Describe what's going to happen. What's going to happen when all of the particles are initially in the container with this energy profile at this temperature. And then what is going to happen to the relative amounts as the temperature goes down? So the amounts here are being shown on the strip diagram, and we can also look at the current amounts. Initial thought, if I pause it right there, for this exothermic reaction, I would say it's beginning to favor the product side. I have more of the products being formed, and the reactants are going down. They all started really close to the same amount, and I'd say for this exothermic reaction at this temperature, the products are a higher concentration than the reactants. But we can change the temperature. Lowering the temperature. If we look at the strip diagram at this top there, or if we look at the current amounts, what we find is that we've increased the amount of the products. For this exothermic reaction, we've increased the products by lowering the temperature. It's pretty clear with the data being shown right now. What does that make sense? How do we make sense of that with our picture? We found that initially there could be a relatively even, perhaps back and forth, left to right and right to left, when we had a high total average temperature. But then when we brought the temperature down, we ended up trapping or increasing the concentration for those particles that had a lower potential energy. It was more difficult to get over the barrier in that case. And for an exothermic reaction, that means that we lowered the temperature and it put more of the particles then on the product side. So this is one way that you can increase the yield for an exothermic reaction. By lowering the temperature, you're shifting more and more to the product side relative to the reactant side.